G'day guys, in this video I'm going to be showing you how to do a second moment of area example. So here we're asked to find the second moment of area about the x-axis at the centroid for this I-beam just here. And just to make it abundantly clear, our axis is located right here at the centroid like that. Okay? Now before I go into solving this problem, I just want to allude to the fact that you might be tempted to try and solve this problem using the integral of y squared dA is equal to ix. And this is the definition of the second moment of area, but I strongly recommend you don't go down the calculus heavy path, because this particular shape isn't very friendly to deal with. It's constructed of three separate rectangles, so to do this using integrals would be very, very messy. Instead, I strongly recommend that we use a few other formulas for rectangles. So let's say we have a rectangle like this of base b and height h, right? If we have a axis located at the centroid of this rectangle, then we know, and I have shown this in a previous video, we know that the second moment of area about the x-axis at the centroid is given as 1/12 base times height cubed. We've shown this in a previous video, and I'll even draw a bar above that to indicate that this is just at the centroid. So we're going to be using this formula a whole lot to solve this problem, right? But another formula that I really want to show you, which will be really helpful, is the parallel axis theorem, which states that if we've got a parallel axis, like say this one, right, I'll call it x dash and y dash just here, then we can find ix dash, right, by using the parallel axis theorem, which says that this is going to be ix bar plus ad squared. Right, where ix bar is exactly what we found before, right? It's the second moment of area about the centroid, about the x-axis. And ad squared is, well, a is the area of the shape in interest, which in this case is just bh because it's a rectangle, and d is the perpendicular distance between the axes. So in this case, d, our d value, would be this distance, whatever it is. This would be our d value. Okay, I feel like that's enough background now, because that's all the information we need to start solving this problem. The way I'm going to start solving this problem, though, is I'm going to deconstruct this I-beam into three separate rectangles. And to make that clear, I'm going to redraw the I-beam down below. I'm going to construct it into... I'm going to construct it into three beams. I'm going to call one beam this one, just here, and it's going to be this rectangle from here to here. And I'm going to get a second beam. I'm going to call this beam 2, so this is our second rectangle, and it's going to be from here to here. And then I'm going to split it into a third rectangle just here, and I'll call this rectangle 3. Like that, right? And we know that if we simply find the second moments of areas for each of these three rectangles and just sum them up, right, we'll get our answer. Okay, so let's do that in slow motion. We know that ix bar, so that's what we're trying to find, is going to be equal to the second moment of area of this green rectangle plus the blue plus the orange. So let's do the green first. We know it's going to be 1/12 times by base times height cubed, which in this context would be 300 times by 50 cubed. So let me write that out for you. It's going to be 300 times by 50 cubed, right? And so what we've done here, what this refers to right now, is the second moment of area about this bar's own centroid, right? But we're not interested in that. We're interested in finding it about the centroid of the I-beam completely, right? So we need to use the parallel axis theorem to find out what the second moment of area is about this axis just here. So we simply add that to ad squared. In this case, a is the area of the green rectangle, which is 300 times by 50. And then we times that by d squared. Now d is the distance between here and here, right? And you can tell that this distance will be 25 plus 100, so just 125 millimeters. So we're timesing that by 125 millimeters squared, right? As you can tell, I'm leaving everything in terms of millimeters, and the final answer will pop out as millimeters. Okay, so in terms of millimeters. Okay, so that's the green part, right? We need to add that to the blue part now. So let's add that to the second moment of area produced by this rectangle, which is what? Well, we'll use this formula again. We know this is going to be 1/12 times by base times height cubed. In this case, the base is 100 millimeters, and the height is 200 millimeters. and then we cube it. Now, you might be tempted to use the parallel axis theorem here, but there's really no need, because we found this value, which refers to the second moment of area about the axis of this blue rectangle, which is perfectly located on top of our centroid anyway, so there's no need to invoke the parallel axis theorem if we liked. I mean, you could, but our d value would just be 0. Okay, so that's the blue bar done. What about this orange bar? It won't be too hard. We just add this entire thing to 1/12 base times height cubed. In this case, our base is 300 millimeters, and our height is 50 millimeters, right? And then we have to invoke the parallel axis theorem again, because what we found is we found the second moment of area about its own centroid, so we need to find this d value again, right? And because this thing is completely symmetrical, I've chosen a fairly simple I-beam, we know that this distance right here is also 125 millimeters. So we're going to add this to the area, which is 300 times by 50 times by 125 squared. 125 squared. And I promise you, if you plug this into your calculator, right, you will get this result. 5.42 times 10 to the 8 millimeters to the power of 4. That is your answer if you plug all of this into your calculator. And this is actually our answer. Now we can choose to put this into SI units if you like by using a simple conversion, but I'm just going to end the video here knowing that this is actually our answer in terms of millimeters to the 4. Okay, so before I end this video, let me summarize everything I've done. What I did is I deconstructed the I-beam into a whole bunch of different rectangles, found out the moments of inertia, or second moments of area, depending on what you want to call it, for each of these rectangles, summed them all up, and that was our answer. I hope that made sense, guys. Cheers.